It's a very, very nice environment, and I think it's a very impressive activity which you are establishing here, and it's really my pleasure to share with you some thoughts on the future of power electronics, which I had also for an earlier conference this year, and which kind of summarizes my point of view in that area, which is power electronics, but as we will see later on, it's also power systems. So, and we, I think, need to bring both areas closer together than what we have today in order really to continue a very dynamic development of power electronics. So I would like to call it more not just the challenges. Of course, if there's challenges, there is opportunities. I think we will find this along the presentation, and I would like to call that whole topic Power Electronics 2.0. And I would also like to acknowledge some contribution of a postdoc of mine, being always interesting partner for discussion, and also of Hans-Peter Näh from KTH in Stockholm, who frequently visits us in Zurich, and it's always a nice discussion with him. A brief outline of my talk, as you see here, it's application areas and performance trends. So this is what I think we should look at first. And next, the question is, what degrees of freedom do we have left for really pushing the technology further? And that goes with components and topologies and design and testing procedures, which are also of really high importance if we aim for a higher level of integration in future. And then the future challenges with the link to the power systems, as we have mentioned already, and all that of course translates into some challenges for university research and education, and finally some conclusions and some outlook. Application areas and performance trends. I always find this a very nice picture because it's from the Tesla. And there is a Tesla manufactured by robots, so an EV car manufactured by robots, which are heavily relying on power electronics and drives. And this is just one example because, I mean, of course, you have power electronics and drives in industry automation and any industry processes, induction heating, for example. Communication, information, data centers would not be possible without the power supply, of course, down from the medium voltage to the really chip level in the 0.6 volt range. Transportation, meaning traction and hybrid vehicles or EV vehicles in EVs in future. Lighting, I mean, if you look around here, there's lots of power electronics around you, so you can easily say it's really everywhere. And what are the performance trends? I mean, if you talk to industry, it's costs. Clearly, the costs need to be reduced. Given a certain state of the art we have today, cost reduction is always a target. Then, of course, losses, which come into play more and more with the concern on the utilization of the resources which we have. So high efficiency is clearly a target. If you aim for mobile applications, aircraft, for example, weight is a big issue. Power density, of course, the same. But failure rate, of course, is also very important, and time to market is a very important figure, especially in the power supply area. So this, I think, shows very nicely how the performance is pushed forward. And it's also interesting that you, of course, need to think that you just cannot push the losses down, but there might be some influence on other performances. So there is a coupling between the performances which you need to understand and also need to highlight in some publications. So it's not just that you can push into one dimension without affecting all the others. And I think in future we might be also discussing other issues, not just the losses, weight, volume, but something like how much of kilograms of iron are you using in order to build a 1 kilowatt converter, or how much kilogram of copper or aluminium, if you talk about a heatsink, or area of silicon or silicon carbide, any wide bandgap semiconductor. So I think those are also interesting figures which are not at all part of our thinking for the moment and not really addressed in research at universities too much. And so those performance trends. But what have we seen, say, starting 20 years ago, and how did those different performance figures develop over the years. If you look at power density, for example, over a time scale of, say, starting from 1980 to 2010, 2020, this is telecommunication power supplies, meaning a rectifier stage active and a DC to DC converter connected in series, outputting typically 48 volts. You found a trend in power density. You can just say it's a factor of 2 over 10 years, very roughly. I mean, we are reaching today 3 kilowatts per liter, and you have to keep in mind that this is a power supply. It's not an inverter. So if you see a figure advertised 30 kilowatts a liter, and you talk about an inverter, it's clear, because all the inductive components are in the machine. You just have the chips, the gate drives, the heatsink, and maybe a fan or a cold plate if it's water cooled, and then you exclude all the heat exchanger to the ambient, and then you can reach a very high power density. It's not difficult. 100 kilowatts a liter have been shown by car manufacturers or by research universities. But if you talk about the power supply and you talk about high power density and high efficiency, then it's a completely different story. And we are currently having something like 3 kilowatts a liter at 97% efficiency, and it's targeting now 98% efficiency, keeping the same power density. But this is a trend factor of 10 over 10 years. This is a rough figure for power supplies. And just to go back, I mean, you see water-cooled systems, this is air cooling here. Water-cooled systems are in the 10, 20, and Fraunhofer or others have demonstrated 100 kilowatts a liter range. Second performance is losses. You should maybe call it inefficiency, not because that sounds more nice. I mean, inefficiency is how people from the US maybe would put it, and losses have been continuously decreased. Again, looking at telecom rectifiers, in 1995, a typical telecom rectifier was 92% efficient, 8% of losses. Now, in 2005, 10 years later, it was something like 95, 96% efficient. Today, we have 97%, so it's always cutting the losses in half over roughly 10 years, 5 to 10 years. This is, again, something which you can see as a trend. But of course, there is a limit down here somewhere. Lower than 0% losses is difficult to achieve. So if you move further and further up, it's more and more of a challenge, and it's less and less return what you get. Costs. Looking at PV inverters from SMA, this is some figure they published. This is the specific price here of the inverter systems. Again, it's something which is kind of cut in half over 5 to 10 years. You see, it's going from something like 0.75 here down after 10 years, it's going to roughly half of it. So there is also a continuous trend for cost reduction. And it's benefiting also from economy of scale, of course, because this is the production quantity which they have. I mean, at the moment they are not doing so well, but that is a different issue. So you've seen the performances and how they developed. And the question is, what degrees of freedom we really have to keep that trend and to push things continuously further. And I think we need, of course, if you look at the power supply, and this is a power supply and not an inverter, so you see there is switches, there's passive components for filtering, capacitor, for example. If it's single-phase mains, you have the pulsation with twice the mains frequency. Clearly you need storage. Then you have inductors, some rectifier diodes, some EMI filtering. I mean, we are doing switching mode operation. For that reason, we are shifting part of the power we are processing up in frequency, and that needs to be filtered out finally. And this is roughly the same amount of power than what we are really delivering to the output. So this EMI filter typically has a 20, 30, even 40% sometimes volume share of an overall converter system. It's not neglectable. So we need to look at all those things. Components, meaning active components, passive components, topologies, because there might be other circuit structures which are doing the same jobs in a better way. Modulation and control, Design procedure, also important. If you aim for time to market, you need to be quick and need to address all things simultaneously at the best way. And modularization, standardization, I think this is another option in order to aim for economy of scale and push the costs down. Manufacturing, so to design for manufacturing, this is more things which are not so prominent in research for the moment, but I think in future will be very important aspects. And of course, we could look for new applications in order to widen the application area and then have again an economy of scale benefit. Components, what are their potentials and what are the limits? And let's start with power semiconductors. And of course, there is silicon and there is wide bandgap semiconductors. And for silicon, it's interesting to see, and this is a chart from Infineon, and this is IGBTs here, and this is power MOSFETs. And again, looking back kind of 10 years, 20 years, you see the improvement which happened with IGBTs. This is the on-state voltage at the given current, and this is the time scale here. You see there is a certain improvement, 60% improvement compared to more or less the starting date where IGBTs were introduced in 1990 roughly. And there is a further improvement to expect, but it's maybe 20–30%. There is still something to gain, but it's certainly not a factor of 10. So we are reaching a kind of limit there. Power MOSFETs, introduction of superjunction technology, you can see it here. This is the specific on resistance over time, nearly a factor of 10 improvement. Here again, still potential for improvement. Infineon mentions factor of 30, a factor of 3 even, depending on the pitch size of the cells which they are implementing, but it's more complicated technology and it's higher in cost. So there is again a trade-off concerning manufacturing costs. So IGBTs benefited from transient field stop technology, which allowed this decrease in on-state voltage, and MOSFETs from superjunction technology. And if you look at the generations, the C6, C7 of superjunction, this is specific on resistance, so there is ongoing reduction, and this is a figure of merit of switching losses, and also the blue one is the state of the art, the red one, the next one, you see it also for the IGBTs, still improvements, but I think the more important aspect is how those components are packaged. Because the performance of the device, or say the chip is there, but it cannot be utilized because the package is just not designed to the application. So I would more see, and if the chip is shrinking more and more, like you have seen on the last slide, so then you have more and more an issue of thermal management, and you need some heat spreading, and the package, I think, needs to be designed properly. For that reason, low inductance packaging, low thermal resistance packaging, advanced low temperature joining techniques in order to have high thermal cycling reliability. So those are, I think, the issues, and I would more see the challenges in packaging, especially because semiconductor companies are basically doing the jobs and we are only using the devices. So the merit is with the semiconductor companies for the nice devices, but we can think about the nice packaging. And what we will see, and there is different trends, and I, for the interest of time, can highlight just very few of them, but one is, of course, that the printed circuit board will be more multifunctional in future. I mean, there will be thicker copper tracks which are embedded in the printed circuit board, some heat extraction system here, all different kind of interconnection technology, maybe also optical interconnection, and it will be interesting to design such systems because you need really a nice design tool to figure out all the parasitics and also the thermal path, equivalent thermal resistance which you have for such kind of structure. It cannot be done in the simple form we are doing today with a heatsink, for example. So for that reason, I would think there is a substantial change in manufacturing process, and I call it fabless power electronics because the universities or researchers might do the design and then some highly specialized company might do the implementation. So it will not be happening, I think, in the same environment anymore, or could be at least. We built a converter for automotive applications together with Infineon, and Schweizer Electronic is a PCB manufacturer, a very innovative one, and we embedded the chips fully into the printed circuit board. So if you look at the printed circuit board, I just show it to you on the next slide. It's a 32 kVA converter, 700 volt DC link, outputs a frequency from 0 to 800 hertz, and it's 20 kilohertz switching frequency. It's designed to really fit on that electric motor here, and you can see it here. So this is the IGBTs, they are embedded. This is the anti-parallel diodes here, and the gate drives are on top, still sitting on top of the PCB, but in future all electronic components will also be fully embedded into the printed circuit board. So it will be a clean surface with all components embedded, and there are, of course, several issues with this technology. On the back side here, so this is this area, on the back side you have the interface to a water cooler. But this is extremely compact and a very nice technology, extremely low inductance, and for that reason, certainly one of the options in future. Another interesting technology, and I just kind of focus on those which are really, you could call it disruptive, in the sense that they have a significantly higher thermal cycling capability than a solder joint, and this is low temperature joining techniques like Semicron introduced already in 2008 here at the CIPS conference, and they are soldering the chip to a flex print here. This is that print here. This is so it's a sinter joint, then the chip is sintered to the DBC, and the DBC is sintered to the heatsink. So there is all interconnections are sintered interconnections, and for that reason they have an excellent thermal cycling reliability and very low inductance because it's a flat structure, and they go in the next step for also integrating the gate drive into this power module as one of the options. This, by the way, is a 600 volt, 400 amp half bridge module which they built. And just talking about gate drives, and I think in future we will more talk about not a switch in a package, but about the switching cell in a package. And that means maybe, of course, two switches, like a half bridge, then maybe some passive component joined to it, maybe also some EMI filtering even. You could call it an electromagnetic quiet package, but also an active gate drive might be included in order really to allow by software only to adjust the switching speed. And what we built, for example, for an IGBT, just to show you an example here, you can measure via the parasitic inductance, as long as you have one, you can measure the dIdt. Here you can, via a capacitor, measure the dVdt. And if you talk about inductive switching, always the dIdt and the dVdt happens one after the other. For that reason, you just need a single controller to implement it, and those loops are kind of naturally closing one after the other. And we built it, and it's an FPGA here, which is much larger than what we actually needed. But this is the power supply of the gate drive, just to give you an impression how it looks like. But this is the performance you can achieve. You see, for the turn on, for example, the voltage goes down here with a certain slope, and the rise of current can be adjusted, or you decide to keep the rise of the current, rise of the current, the dIdt the same, and the dVdt should be adjusted. So you can freely adjust the switching behavior, and this is a very nice performance which in future could be built into a component and makes the utilization of the component much more easier than what we have today. This is silicon, and I think there is still a lot to do, especially concerning the packaging. Also, the devices will, I think, further improve. Of course, it's not just wide bandgap, but of course, wide bandgap is one of the coming and really high potential technologies. Again, specific on resistance, now shown over the voltage. This is the silicon limit. There is the silicon carbide limit, there is the gallium nitride limit. If you look at this, there is a significant decrease which you can have in on-resistance. For that reason, it's really highly interesting, because with very few technologies we are using in power electronics, you have this massive improvement like you have with the wide bandgap semiconductors. Digital control, I think, might be another one following Moore's law. This is the two areas which really give a push to the whole field. So extremely low on resistance, then very high junction temperature, which would be possible once you have the right package, and extreme switching speed once you have the right package. So, I would like to show you this little video here, because it's even the President of the United States talking about Can you hear?
And the companies that figure out how to do this best, they're the ones that are going to attract the jobs that come with it.
Okay, I mean, he should know. But he was not talking about packaging, so which is very important, I think. Yeah, I'm sorry that it was difficult to understand, maybe, but just let me clip my mic here again, which is also a delicate piece of equipment. Okay. Okay, just a second. Okay, here we go, I think, yeah. Okay, now you have different perspectives. So there's silicon carbide, but of course gallium nitride is coming. And by the way, those slides will be later on some web page. So if you would like to look at the video again, then please just refer to this version of the presentation. I mean, this is some prediction. There is market studies, of course, and this is a kind of balanced view. Gallium nitride at the lower voltage end, silicon carbide at the higher voltage end, and here going further. I mean, if you look at Japan, and there was a conference in Hiroshima in some months ago, and it was really interesting to see Japanese manufacturers, Mitsubishi, for example, or also other Hitachi, showing devices, 3.3 kilovolts, 400 amps. Or 100 amps. So not a small device, but really something which is already packaged in a module and which targets, for example, traction or aircraft applications. And this was really kind of where you could have been uncertain whether this is really some direction to go, but it seems that one of the main companies are, without compromise, pushing it further quite strongly. So for that reason, this is the kind of balanced view. But if you're a superjunction manufacturer, then you might want to see this in this form, or if you do a silicon carbide component, you might see it in this form, or if you're gallium nitride, you think it's all over the place, and all the rest just forget maybe a little bit of superjunction and silicon carbide device here at the edge. So for that reason, I think it's still not decided, while gallium nitride clearly has a very good performance here. Silicon carbide, once it goes above a kilovolt, I think there is not too much choice for the moment with other components, and if you need a high switching frequency. I think what is important, and this is just to show you two further examples of packaging, that you can have, or you will have a package which really allows you to utilize the switch. And for that reason, it's just an example, 600 picohenry DC-link inductance achieved by Fraunhofer for the packaging of two silicon carbide JFETs here, which are laminated into a printed circuit board and directly attached to the DC-link capacitors, which are ceramic capacitors in this form. And I think this is what I found very interesting also, was also shown at the CHIPS conference this year. It's from Panasonic, and it's, Nottingham is matrix converters. All people know, of course. And this is a matrix converter with monolithic bidirectional switches. It's claimed to be good for 5 kilowatt motor supply, 600 volt 10 amp devices, and they have a drive-by-microwave gate drive technology, which is extremely compact and directly joined with the switch here. So the whole thing here, 5 kilowatt, is this footprint. And if this is the direction to go, then as a university you really have to be concerned, because you need to catch up in technology quite a bit compared to printed circuit board manufacturing. I mean, that goes also with our university, of course. And, but it's something which I think nicely shows what could be possible in future. And also the design of something like this is completely different to a conventional converter design. So to summarize, power semiconductors, gate drive packaging, I think there will be main challenges for module manufacturers, like this electromagnetically quiet package which we mentioned. Then the gate drive, which could be more advanced than what we have today, and especially also concerning ensuring reliability and also test procedures of devices which are nearly not failing anymore. And the challenges for the general user will be the high level of integration, like PCB integration or what we have just seen at the last slide. And there might be a fundamental change in design, manufacturing process, and also measurement technology, because once you have it integrated so tightly, you are not able to measure anything but voltages, no current or something like this. Temperatures are also difficult to measure on the spot. Passive components. Capacitors, magnetics, cooling. I think I need to be very quick here in order to cover all my slides here, but I think just to give you a feeling, this is from 2000 to 2010. It was published by an automotive company. This is the decrease in volume which you find from capacitors. It's roughly cutting in half the volume with a nicer packaging, a little bit of a reduction in foil thickness. This is the foil thickness which is shown here. For the electrolytic capacitors, it's not so much of a change, so there is not a really significant improvement in power density concerning foil and electrolytic capacitors. And also here from EPCOS, for example, energy density in the year 2000, foil capacitors 100%, 2015 predicted 120%. Interconnection technology and packaging. Now you can find capacitors which have a flat interconnection, which are very low inductance. You see the switching over voltage here, which goes down significantly. So there is a somewhat lower volume, but we are not talking factor of 10. We are talking maybe 20, 50%. So it's really kind of not so much. And there is low inductance busbar connection and low switching overshoot. I mean, now that the components are more designed to our need, what you could think of in future is that you are monitoring certain components, like an electrolytic capacitor. This is the impedance of the capacitor. So this is the region where it's kind of series resonance with the equivalent series inductance. And if you monitor this resistance here, so that is after some time in operation increasing, and you could use this for lifetime prediction, and you could then have some bus connection of all the components or just an RF link to some central control. So there is options, but of course it's costly, it might be not reliable, so there is all different kind of issues, but that could be a direction to go. Magnetics. I think this is something, there is no Moore's law in power electronics because the scaling laws are different. And I think this is what is important. I mean, Moore's law, and it also has been shown yesterday, you see this nearly the doubling of the computational performance every 18 months or 2 years. So, but if you look at our scaling laws here, this is for a transformer, the area product here. So this is more or less the physical size of the transformer. Then this is the power to be processed, and this is operating frequency, flux density, current density, depending on conductivity of the material, and that is not going to change. Copper, alumina, I mean, you could say nanotechnology, this is the future, of course, there is some promise, but for the moment we are stuck here, also with flux density, not too much, and here, especially if it's joined with frequency, if you push higher in frequency, so then you see that this is not going to work easily. So we have a technology here which is kind of slow. And developing over 10, 20, 30 years. It's material research. It's not some fancy other type of technology. So for that reason, we have serious limits still in frequency. If you allow a certain loss per volume of a magnetic core, you have a saturation limit here at the lower frequency end. This is frequency, and at higher frequency you need to reduce flux density because there's this Steinmetz equation, and then you see that the losses go up with frequency, so you need to reduce the flux swing. So you are limited with the magnetic core, and you are limited with the winding. If you have a solid wire, there is skin effect and proximity effect. If you split it into strands, meaning using a Litz wire, you can improve significantly. Finally, there is the inner proximity effect of the Litz wire, which then makes it more worse than the solid wire actually at very high frequencies. Or you go very high number of strands, which is very expensive and very low utilization of your winding window. So for that reason, you have a kind of frequency barrier, you could say, here with this effect and this effect. And for that reason, if you build a transformer, and you say, okay, I allow any frequency, but you will find that somewhere around between 100 kilohertz and a megahertz, there's a kind of minimum volume and minimum loss point. So if you push higher, there is not so much to gain. And I think this will be a real challenge with gallium nitride allowing 10 megahertz or 20 or 50 megahertz of operation. What kind of magnetics are we going to use? I think this is a real challenge which we need to address. And it's also interesting because magnetics still account for quite a large share of the costs of our systems. This is UPS systems, 20 kVA system. This is the overall cost distribution, and this is the power stage here, again shown here, and it's 40% of the power stage costs are magnetics. So for that reason, our little friend here is sitting on a pile of money, and we need to find some solution to get him out of the picture here. So capacitors and magnetics, comparably large volume share and cost factor, as we have seen. For the capacitors, some promise that you have advanced dielectrics in future. For the magnetics, the careful design is absolutely mandatory. I think this is very important, and it's not really well addressed in research publications, I would say, and even at universities. I think the people who very well understand all the high frequency effects in magnetics, you can count them with two hands easily in Europe at least. And improved heat management of magnetic components is also something which allows us to shrink the component, not necessarily the losses. Converter topologies, because you might say, okay, power semiconductors, not my business, I package it nicely. Inductors, I have to accept what I have. Capacitors, a little bit of improvement, but topologies, that is the way to go. And if you look at topologies, 1944, you find 6 switch converters, and I think that has been shown yesterday also. So it's something which is around for quite some time. You even find push-pull converters. People thought about high voltage DC transmission at this time. So you can see it here, DC link for transmission line, that was thought to be a high voltage transmission. So it's concepts which are rather old, and the topologies have not changed so much. Also for single phase power factor correction, you see an AC single phase source here. This would be the output capacitor, and this double boost topology, which has been heavily advertised in literature and research around 2000 to 2010, it was patented in 1983. So it's more kind of rediscovering or reinventing topologies which have been used already, but if you look at it, it's the most simple concepts which you can find, which finally make it into industry. I mean, you could say, okay, I have some basic structures like a buck-boost converter here, and I build some auxiliary circuits around it in order to improve the performance. But if you check it overall, if you use the same silicon area here, like in both circuits, the efficiency curve which you find over the output power is not so much different. So you are building auxiliary circuits, you have more complicated control, but you have, of course, also additional losses in all your components, and finally you are nearly wasting all that power you are gaining from the power stage you are saving in the main power stage, you are then finally kind of wasting in the auxiliary circuits. You could think of integrating functions in order to get it more compact and get it more or less expensive. Two-stage conversion or the matrix converter, I think very delicate trade-off which needs to be looked very closely, but in general you could not say that it's always a benefit. Certain areas yes, several other areas no. I think one direction which would be interesting to look at is to split, not to integrate, but rather to split different functions in very dedicated functions which are highly optimized. And this is some trend which you can find in telecommunications. Vicor, for example, prominent company in that area, they are really having dedicated blocks like DC-DC converters which just provide isolation but no voltage control. You could call it a DC transformer, because input-output voltage is fixed ratio and it's just isolation. And this has 99+% efficiency. And then you join it maybe with a converter which does some pre-control of the voltage, and then you are fine at the output here. And this is maybe at least one or the direction to go. So I would put it like this: new topologies, there's not so much. I mean, there is exceptions, as always, of course, multi-cell converter systems. This is some direction which has not been so well analyzed, especially for higher power, higher voltage applications, and some buck-type interfaces and some more here. So multi-cell converters, I think, very prominent for the moment also. This is something where you really could have a contribution, still parallel interleaving, series interleaving. Just to show you an example, I mean, you are not using a single stage here, but you split it, and if you just have to deliver low power, then you just operate one stage, so you can keep a very flat efficiency curve down to low power. If you switch all of them, then there is a cancellation of the ripples here if you do a nice interleaving. So for that reason, you can have here low inductance values and still achieve a very smooth output current. So there are several advantages, and of course it's all the same stages. For that reason, there is some kind of economy of scale also in this form, and redundancy is also something which is offered, and serious interleaving is a kind of dual approach and is not so well analyzed than parallel interleaving. So examples of multi-cell converters, of parallel interleaved circuits, just to show you a little bit of the potential. We built a very highly efficient system for AC to DC conversion, and we just wanted to push the efficiency to the maximum, and what we found is something like 99 plus, nearly 99.4% efficiency, but at the comparably low power density. And if you do it right, you only need silicon superjunction MOSFETs. It's not that you would need silicon carbide devices necessarily. So this is how it looks. I had 6 phases interleaved, foil capacitor instead of electrolytic in order to also save losses there. And this is another example. You see it's only 3 systems which are interleaved, but now it's more a compromise. It's built for higher power density, and then you can only achieve lower efficiency. And you might say, okay, 4.5 kilowatts per liter, but you have heard about 30 kilowatts or 50 kilowatts a liter. But look at that system. I mean, this is energy storage here, which you need because the single phase mains pulsate, the power is pulsating. You need some storage. This is the storage. Then you have inductive components, which you do not have in an inverter drive because the inductors are sitting in a machine. You need to provide it here. For an inverter drive, you frequently don't have an EMI filter, but here you definitely need an EMI filter. And you can see it's roughly 1/4 of the volume which you have for your whole power converter. So it's not something you could easily neglect. And only if you consider all of this, then you have a working system. And then you end up with power densities in this range and still comparably high. Efficiencies, which by the way are very flat over the output power because you can turn off stages and keep a high efficiency. So summary, topologies, basic concepts are extremely well known and I would think they are mature. Doesn't make too much sense to do research on this. Comprehensive and comparative evaluations are missing. People do not know how to compare those topologies easily, and there is some promise for multi-cell concepts. Control schemes, I think digital control, all different kind of functions you can implement. This is certainly a very interesting direction because it's following Moore's law, getting lower in costs. I think this is something, but the basic concepts are extremely well known and not much to gain. Advanced design, I will go very fast over this one. I think the main point you need to, or I would kind of ask you even to consider in research, not just talk about one figure. Consider at least the second one or a third one, and they are all coupled. I mean, if you talk about reliability, you talk about redundancy, and then it's increasing the costs. If you talk about efficiency or size, size means high switching frequency. High switching frequency means higher switching losses. So then you have to trade off against efficiency. So it's all connected. And I think academic research needs to address this mutual coupling of the performances. Not just look one-dimensional, maybe you should look multi-objective. And the way we try to solve it is that we have some design space which includes topologies and components and all the rest, and then we try to map it into the performance space and try to understand the trade-offs. If you go for high efficiency, as we have seen, low power density here. If you push power density up, efficiency decreases, so you have a certain slope, and this is very interesting to understand for a certain technology. If you improve your technologies, you improve your performance, but how much of this improvement you can gain, I think this is very important, and this would be a typical, in my opinion, a typical subject for academic research in that area. This is what we are aiming for. This is kind of our roadmap. In 2020, we would like to do 80% virtual prototyping and maybe 20% experimental verification. So there is remaining challenges, the comprehensive modeling, EMI reliability. I think this is really a challenge, and also model order reduction, because this is highly complicated equivalent circuits and you need to reduce them in complexity in order to be able to simulate the whole thing. And it might take us a few more years, keep us in research going. And all this, and maybe the last 5 minutes, if you allow me, was kind of power electronics 1.0. Because it's power electronics as all of us know. But I think the question is, what is the next big challenge? Because we have seen that there is certain improvements, but if you have a 99% efficient converter, you can just talk about losses and say, okay, I reduce the losses, cut it in half, but it would not make too much of a difference, especially if your load, for example, is only 95% efficient or 90% efficient. For that reason, I think we also need to look at other challenges, not just in our area. So, and this would be something we need to overcome here. And the way I would like to put it is that we could consider the converters, which are extremely well designed already today in industry, like integrated circuits. And if you look back in analog electronics, it happened in this way 30 years ago. You had printed circuit boards, which are then were an operational amplifier, and then finally they get more and more highly integrated, like in the form we have today. And this also could be done with power converters. At least part of our thinking could be that we go more to systems rather than converters. So the converters could be systems, whatever that is, could be hybrid systems. We have seen a hybrid excavator or hybrid cars or whatever it would be. I think from considering a point in time, we would need to extend our thinking to the integral over time. So meaning from power to energy. In future, I think it will not be that at a certain point in time you can convert power with a certain efficiency, but you might be asked to have a solution which is optimal for a certain load profile or over a certain time span. And for that reason, I think this is, to me, kind of, for our research in Zurich, this is kind of for the next 10 years, the key equation, and a little bit of that down here. And I think we more need to think, instead of power conversion, about energy management and distribution. And the converter analysis, I mean, looking inside the converter, I think you should also look at the interaction of the converter, either to the grid or to the electric machine, high frequency losses, and then trade off both and design both together. Converter stability and all that kind. I think there is already efforts underway in this direction. This is a data center supply, conventional one, input from medium voltage, 480 volt AC, UPS system, and then in the rack, in the server rack, it goes down to 12 volts here, and then finally to something like 3.3, 1.2 volts. And if you look at all this, then you can eliminate quite a lot of it if you do a 400 volt DC distribution, which, by the way, is also higher efficiency. So this is something which is under discussion. Some people, like Philips, for example, discuss plus minus 380 volt DC. So there is ongoing discussions on this. Still no solution, of course, but it's interesting. This is one area. Think about the energy supply chain. I think the second one is to think about, once power electronics is migrating into the grid, to really think about stability problems, because this is frequency 50 hertz down. This is the traditional power systems area, but this is the range where we would typically be operating with kilohertz or 100 kilohertz switching frequency. So for that reason, we need to bridge that in some way and join the thinking of both areas. So our performances, I mean, same diagram, but different figures here. I think we will go to total cost of ownership over a certain life period of the device. Failure rate, still important, of course, floor space requirement rather than power density of the individual converter, manufacturing and recycling effort in future maybe, and some mission efficiency or mission energy loss, not just at a certain point in time. So the system-oriented analysis, in order to summarize, I think we need to get to know the details of the power systems. I think we should, as power electronics engineers, should start to bridge the gap. From the power systems people, of course, would be nice if we can join and meet in the middle, but we could start. And we need to understand certain issues there, like autonomous controller, stability of converter clusters, and all that forth. So just a few remarks on university research. Often, and I think with the center you established, it's completely different, but what you often see is a kind of disconnection between university research and industry. So, and that gap definitely needs to be bridged. Also for the reason that in future universities will rely on the technology partnership with industry, because only industry might be able to offer that high level of integration which really is needed. And an interesting aspect in that context is also that if you talk to industry, to list the first three priorities, what is important? And it's costs, costs, costs. And if this is the university here, costs is not part of our picture. I mean, there's a good, of course, also a good side of it, but I think once you are working in a mature area, and power electronics in certain areas is maturing, then reliability and costs are the main figures. And if you would like to do research in that area which has an impact, you need to show costs. You need to show how competitive you are against an existing approach. If you go into a new area, new application, it doesn't matter. But if you would like to just push someone out of that area, I think you should at least think of how much of material I'm using, and then I can calculate how much this is going to cost. And it's also interesting concerning the technology partnership. This is what industry is offering today. So we are talking power densities even of power supplies which are 15 kilowatts per liter, excluding heatsink. This is advertisement. But it's white core, for example, and this is something, if you would like to do competitive research at universities, you would need to be able to beat this. And this is nearly impossible. This is a concern. You could say industry is leading the field, partly at least. And this is something where universities really need to ask, what is our contribution? So, I mean, the way we are approaching it in Zurich is we kind of will keep out of this area in future, which is this middle power range. We will go more high power. We call it mega power electronics, medium voltage, medium frequency. I think this is the key words there. And we go micro power electronics, which is joining microelectronics technology and power electronics. So this is the two directions. And of course, if you go up here, you need to bridge the gap to the power systems people. This is extremely, extremely important. And concerning education, I think what you have seen, it's kind of interdisciplinary field. And for that reason, I mean, this is the only keyword, but of course, the individual, the core subjects need to be taught in the very details still. But there should be some kind of integration of this knowledge, if possible, so that it's already happening at the university and not later in industry only. And especially, I think, joining power electronics and power systems, this is both electric engineering areas, this should be especially easy, you could say. And of course, lab courses are very important also, not just theoretical analysis. So Power Electronics 2.0, I think this is, if you look at the technology S-curve of power electronics, I mean, you had thyristor here, then the power MOSFETs, IGBTs, and digital control. I think this was a main contribution for this step here. Superjunction and wide bandgap giving the next. And you then would need to think how much we can push up here. And I think one limiting factor will be passives, including packaging, interconnection, and advanced design in order to relate all the different pieces together. And it might also be costs, and certainly it will be systems. So this is something we really need to address, I think. And I think you could see two directions of development for power electronics. I mean, we are here, kind of here. One will be where the performance is sufficient and you spread it into applications and go for low cost, basically, with a certain performance you already have today. And the other one, this you could say is a market pull. Smart grids, green smart buildings, hybrid electric vehicles. Or you have a technology push, which is then benefiting from wide bandgap semiconductors, digital control, and some advanced design and packaging, which brings you higher in performance, but maybe also costs. And then this will finally spread into certain applications. So this is kind of the two trends which I would see. But we have reached a very high level of performance, and we can easily spread it into a system and get a large benefit. So to summarize, everything will be smart. I think we have seen it yesterday also on some slide. I mean, it will be an integration of energy and power and information communication technologies. But I think this is important for, say, the next 10, 20 years of dynamic development of our areas. We need to go from converters to systems, from inner function to interaction analysis, and from power to energy. And we need to bridge the gap. And if you have any questions, then I would be happy to answer if you're not too tired. Thank you.